All right, so we've gone over doing sample data, and we saw how the degrees of freedom changed how we do variance and standard deviation. Now we're going to take a look at how does having a small sample with an unknown population standard deviation, how that affects we do our hypothesis testing. So the t-distribution, it works very similar to the normal distribution or the z-distribution. Our data will be close to normal, but our sample size will be small, okay? So, and we're going to use the t-distribution again when we don't know the standard deviation for the population. And just a word on this, we don't know really, statistically, we aren't ever going to know the standard deviation for the population or the mean for the population or any statistic at all for the population because we just aren't going to be able to collect all that data. Now, of course, at the population, we're just very small to begin with, and now we're very, very narrow. Like we talked about when we were setting up experiments, how we want to be very specific in how we frame our test. We might end up with a very small population. Like we might say, our population is just the students at the school. Then, well, that's small. That might be possible depending upon the size of the school. That might be possible in that case to actually get the statistics for the entire population. But in general, our populations are actually really large. Like we're working for a company and we produced a certain number of computer chips, maybe 100,000 computer chips. We aren't going to test all 100,000 computer chips. We test a sample of them. Okay, so some characteristics of the t-distribution. It does have fatter tails than the normal distribution. We'll see that in a minute. And it's going to account for the degrees of freedom like we talked about before with sample statistics. And there's no set rule for when to use the t-distribution, except for it's kind of globally accepted that if you don't know the sample statistic for the standard deviation or the population statistic for the standard deviation, then you should use the t-distribution. But sometimes it's close enough to normal that we don't need to. So here's a picture. This one in red that I'm tracing, that would be like normal. And the t-distribution is below it. And for a very small sample size, you can see, well, that's not even close, right? Its tail ends are way fatter. Its center is not as tall. And that's absolutely true. For small sample sizes, it is not even close. But as you get larger sample sizes, that's what this picture over here on the right is about. As we get pictures or a sample size that's close, 30 or above, it gets very close to normal. Like you can't even tell right here that there is a difference. Now there is a difference, especially over here. Like if you look at the light blue and like that black drawing, it's close, but not exact. The tails are still fatter. So as you get further and further away from the mean, the tails are your data is going to be more off. But that's a comparison, and of course you can see like as the data gets larger in size, we get closer and closer to the normal curve. So when are we going to use the t-distribution? Well, it varies. It depends upon your textbook. It depends upon your class. It depends upon the situation. So this rule is for this class. It's not for any other statistics classes. It's not for any other situations for this. It's defined by, whoever is basically in charge. I'm in charge. So this is how we're going to do it. So we start with this question. Is the standard deviation known, as in for the population? And guess what? The answer to that is usually no. We don't know that. So we'll generally come over here. No, it is not. So then we're going to ask the follow-up question. Is the sample size less than 30? Okay, now we have two possibilities. If yes, okay, then we are definitely doing the t-distribution. If no, then we can approximate with the normal distribution, or z. Now, what changes for this? For us, we've been using for our z-score, when we're doing hypothesis testing, we've been doing this. X bar minus our claim all over our sample standard deviation square root of n. And this actually stays the same. Our t-score is exactly the same. Is going to give us the same thing. What's going to be different is when we go onto our calculator, when we go into distribution, instead of selecting normal, we're going to select t. And there's going to be a few differences there when we actually do it. So let's do 3 examples. Mr. Shao collected data on possible basketball recruit after 10 games. So notice our sample size is 10. So that tells us right away t-distribution. I mean, unless we know the standard deviation for the population, so this basketball, all their basketball. Now, could we get the data for all the games of a basketball player? Sure. In this situation, could Mr. Shao collect that data, like go in and find that? Yeah, he probably could. But he has just collected data for 10 games. And it shows that the player scored an average of 25 points with a standard deviation of 6. So this 25 right here, that's our X bar, and this is our S. To get an offer, a player must have an average of 27 points. So it looks like face value, this kid's not going to make it. He's not going to get an offer to play ball for Mr. Shao. Can this player receive an offer? We're going to use a 5% significance level. Okay, we're not going to give him very much leeway, right? So let's draw a picture of this test and also get our hypothesis down. So we have our null and alternative, and just like with the z test, we're going to identify these the same. A player must have an average of at least 27 points. So mu is greater than equal to 27. This is our claim. Now, how do I know what the claim is? The player wants the offer, right? So the claim is, yeah, I make 27 points or more. So our alternative is less than 27 points. Okay, so if we're doing a 5% significance, and I won't draw right there, our distribution will just draw it the same as if it were, no, it's not a big deal. This is just for reference. So we're going to do is it left, right, or center? Well, it's a right test, right? It's a less than. So we have this area right here. And this area is 5%, okay, of the whole thing. So let's get our t-score. Now, how do I know I'm doing a t-score? Well, because I don't know the population standard deviation, and nor do I have a significantly large sample size. I only have a sample size of 10. So our t-score is going to be calculated the same way as if it were the z-score. So our sample mean is 25. Our HA, our claim, is 27. And our standard deviation is 6. And square root sample size of 10. And when we type all of this in, we're going to get let's see here, negative 1.05. Sure, we'll give them a little bit. Okay. Now, we're doing a t-distribution now. You're going to go to distribution, on your calculator. But instead of selecting normal, you're going to select T. You're looking for that T. And how your calculator labels this will vary. Okay, so we're going to go into our T distribution, and when we do, we are going to look for an inverse T. This is what we're looking for, inverse T. And it's going to ask us questions similar to if it were a Z. It's going to ask us for an area. It is also going to ask us for a DF, or degrees of freedom. And other than that, it's going to work the same. So our area, now this is where it'll be your area here, it depends on your calculator. So on most Casio calculators, it always, for whatever reason, I actually think this is kind of dumb, but it's whatever. For most Casio calculators, they actually, for the T distribution, do all right-hand tests. And this is a left-hand test. So I'm actually going to have to put in 0.95. But I'm pretty certain, although not like 100% sure, I think TI does a left-hand test all the time. I'll check that later. I just don't have it handy. In which case you do 0.05. Now, here's how you're going to know ultimately if you're getting the right number. Our mean is in the middle, right? And all our scores over here on the left are negative, and all of them on the right are positive. So we are expecting a negative inverse here. Okay, so when we do that, we should get, and you'll have to check this as you're following along to know which kind of test your calculator is doing. But I get a value of negative 1.83 for my score right here. Okay, so what that means is this number right here is negative 1.83. Now, if you did it the opposite, it will give you a positive 1.83. So you can just make it negative, because that's what we're expecting right here, is a negative on the left. So where is HA in relation to that? Well, HA would be like over here somewhere. This is our HA. We calculated it at about negative 1. So HA is outside of the region. So it's going to work just like our Z test. Since HA is outside of the region, we reject HA. It's not supported, which means HO is supported. So with 5% significance, we can say, based on the evidence, let's give this player an offer. And you might be thinking, well, he made less than, 27 points, an average of 27 points, so he shouldn't. But this is a sample. We don't know all his games, and based upon the significance level that we selected, then he actually should make it. He's close enough, right? Let's do another. To be labeled healthy, a food product must have no more than 2 grams of fat per serving. A sample of 12 energy bars. All right, so this is our N. So we're using the T distribution. Have an average of 2.3 grams of fat with a standard deviation of 0.5 grams. Can this energy bar be labeled healthy? Okay, so this is our X bar. And over here, this is our S. So what's our hypothesis? Okay, so these questions are being worded different than they were before, and that's on purpose. It's to get you thinking what is the hypothesis if it's not clearly stated. So we got to think from the perspective of the energy bar company. If they wanted to be labeled healthy, then what is their claim? Well, their claim is that we would have less than 2 grams of fat. It said no more than. So they can have 2, which means our alternative is greater. And this is our claim right here, that they actually have less than, because that's what they want. They want to be labeled healthy. So let's draw our distribution. We draw this picture so we kind of have a frame of reference for what we're doing. And this, let's see, left, right, or center test, this is a greater than. So it's a right test. Did I label the last one right? Why did I label this one a right test? That was dumb. This was a left test, right? Back here. This was a left test. Derp to derp. Okay, so this is a right test. Center is not equal. Center is also a two-tailed test. Okay, so we have some area over here. Let's get our t-score. So that's going to be 2.3 minus 2. We have S is 0.5 divided by square root 12. Okay, so what do we get? Typing it in. And we should get, for our score right here, a 2.078. Okay, so that's our t-score for our claim, our HA. Now we're going to go to our distribution. We're going to do inverse t. Now I want 5% significance again, so that means there's 5% right here. Now on my calculator, when I do the area, since I know that my calculator always is going to do a right-hand test, for whatever reason they programmed it like that, I'm going to put in 0.05. But for you, your calculator may be doing a left-hand test, in which case you're going to do 0.95. In any case, what we are expecting on the right-hand side is we're expecting positive values, not negative values. So we'll just make that adjustment if necessary. And we're going to have degrees of freedom. Let's see, how many degrees of freedom do we have right here? Degrees of freedom. If we have 12, a sample of 12, then we have 11 degrees of freedom. So that gives us a score of 1.79. So that means when we come over here, this number right here is 1.79, and which means our t-score of 2.07 is inside the region. So HA is inside of the region. So HA is supported by the evidence, which means our claim is not. So the evidence does not support the claim. So what does this mean ultimately? This means that no, they cannot be labeled as healthy. Now, that's not to say that we couldn't, like, maybe they contest and say, hey, that was just a bad sample. Take another sample. Then maybe they would be able to reverse that. Now, I want to check back here, did we talk about the degrees of freedom? We should have had 9 degrees of freedom back here. So I don't think I spelled that out right here, but we should have had 9 degrees of freedom over there. But otherwise, the answer is still correct. So I really messed up that first problem. All right, so this problem. Last example, a certain ball must be 40 ounces to be considered regulation. Cheapo Sports did a production run of balls from a sample of 24 units. So this is our sample size, right? This is our N, which means when we get to it, our degrees of freedom is 23. And we want to make sure that's a little bit extra step that we didn't have before. So the average weight is 42 ounces in our sample. So this is our X bar, and this 4 ounces, that's our sample standard deviation. So HO, HA. Well, Cheapo Sports wants their ball to be regulation, so their claim is we make balls that are 40 ounces. That means the alternative is not 40. So left, right, center, this is a center test, right? So when we draw our picture, if it's a center, that means we have two tails. A two-tailed test. Now, I did not specify in this problem the significance level, so we're going to get to choose it. So let's choose a 1% significance level. Well, what's that mean? That means 1% is divided between both sides. So I'm going to have to divide that into 2. So this is 0.5% on the left, and this is 0.5% on the right. And that means when we go to do our inverse T, our area is going to be 0.005. Now, you could do it twice, do one for 0.005 and one for 0.995, but really you don't need to. It's going to be just a difference in a sign. So let's get our T-score. Oops. I don't want to end. Okay. Can I still write? Okay. Shoot. I'm going to keep this, and I'm going to start my slideshow. Okay. I didn't mean to end the slideshow. All right. So T is going to be, let's see here. I got all messed up. 42 minus 40 all over 4 square root 24. So T is going to be 42 minus 40, 4 divided by square root 24. T is going to be 2.4495. Okay. Now when we do our inverse T, we're going to want to put in our degrees of freedom. We're going to do a T-test. And degrees of freedom, 23, yep. We'll execute that. Now we want both a positive and negative number. So we get 2.807. This one will be negative. And this one right here will be positive, 2.807. Okay. And we need to know, well, where's this 2.4? And it's like right here. This is our HA. It's right here. It's outside the region. So since HA is outside the region, we say HA is no go. HO is good enough. So so this was our claim. Should always label your claim. So can their balls be advertised as regulation? Yes. Based upon the evidence, yes. Their claim is not proven, but it is supported by the evidence that has been gathered. All right, this wraps up this section. Sorry for the mess ups. But basically it works the same as with the Z distribution. Just make sure when you go in your calculator, you go to the T distribution instead of the normal.